Hi everyone, I'm Chris and welcome back to the lecture on linear regression of this machine learning course. This final section of the lecture is about regularization. We can try different models and finally select the one with the best scores according to cross-validation. But, of course, there is an infinite number of possible models. This is why regularization is a good idea. Models with a lot of trainable parameters tend to overfit on the data. Consider, for example, a dataset that has exactly 100 data points. A polynomial regression model with degree 99 has exactly 100 trainable parameters. It is able to fit the data perfectly. And for models with higher polynomial degree, it is the same. There are techniques which prevent such models from overfitting. Consequently, the models will give better results even if they would without regularization tend to overfit on the data. So regularization helps to prevent overfitting. One regularization method is early stopping. The idea is to stop the gradient based minimization before the global minimum is reached. We can measure the model fit to data by calculating the accuracy, for example with the cost function mean squared error or mean absolute error. During the iterative training procedure, the training data fits better and better to the model. So on the one hand, the training accuracy gets better and better with every iteration. On the other hand, you could consider some data you left out in training. Such validation data can be used to estimate the model quality on new unknown data. Let's consider the accuracy for the validation data. It reaches a maximum at a certain point. But when the model tends to overfit, the accuracy on the validation data decreases. For this regularization approach, you need enough data to left some data out for validation. There are further techniques for regularization. Another popular idea is to modify directly the cost function. The modification aims to penalize somehow the usage of more trainable parameters to prevent overfitting. Here, we consider the so-called L2 regularization. The cost function is modified by adding the sum of the squared trainable parameters. This sum is scaled by a factor alpha, which controls the strength of regularization. For the linear model, this regularization is called rich regression. Note that the linear model usually only takes the slope parameters of the model into account for regularization. The cost function has now two contributions. One is measuring the quality of the fit. The other is penalizing large values of the parameters. A less influential trainable parameter leads to large values to have an impact on the model. And this leads to overfitting. So exactly that is prevented by the regularization. The parameter alpha is a new hyperparameter of the rich regression model. It can modulate the influence of the regularization. A further commonly used regularization term in the cost function is the so-called L1 regularization. In case of the linear regression model, this gives the so-called Lasso Regression model. In contrast to the L2 term, where the square of the parameters beta is used, L1 takes the absolute values into account. Of course, L1 and L2 regularization terms can also be combined, which gives a so-called elastic net regularization. Here you have two new hyperparameters, alpha and r. They control the contributions of L1 and L2 term to the cost function. More interestingly is the difference between L1 and L2 term in regularization. On the left side, we can see the effect of the L1 term. On the right side, the effect of the L2 term is sketched. The contour lines of the cost function without any regularization are shown in black and blue. These are the lines of constant height of the cost function. So when the cost function has a constant value in parameter space. A contour line of the L1 and a line of the L2 term are shown in green. The L1 term has a diamond shape due to the absolute values. The L2 term gives a circular shape because of the squared parameters. On such a contour line of the regularization term, the term had the same value everywhere. Therefore, we seek for the intersection of the L1 or L2 contour with the contour of the pure cost function with the smallest value. This would minimize the total costs. On the left, we see that this point is on the beta 2 axis. This means beta 1 is equal to 0 at the optimum. On the right, for L2 regularization, this point is somewhere between beta 1 and the beta 2 axis. Of course, this is a very simple example, but in general, the L1 regularization tends to set the less influential parameters to 0 compared to L2 regularization. So whenever you want to find a model which limits the total number of parameters, the L1 regularization should be preferred. Section finished and lecture finished. In this lecture, we considered the regression task and how to tackle it with a linear regression model. Therefore, at first, a given dataset needs to be preprocessed. Then, we choose a cost function to measure the model quality with respect to a given dataset. Using this cost function, the model can be trained with data. The final model can then be evaluated with a cross-validation approach, and the best model out of several possible options can be selected. To prevent overfitting, we can use a regularization technique such as seen in this section. In the next lecture, we consider the logistic regression model to perform classification tasks. Thank you very much for listening. If you liked this video, please click the like button and consider to subscribe this channel. If you have any comments or questions, please leave a comment down below. And thanks again for listening. See you in the next lecture.